It is an unavoidable fact that quantum mechanics is counterintuitive. This stems largely from one principle at the heart of quantum mechanics, which states in part that quantum entities do not have absolute positions in space. In reality, the atoms that make up everything around you aren't point-like objects, but are in fact smeared across a region of space. We can therefore only describe the position of an atom by a wave, because waves have the abstract property of not being located at a single point, but over a length, called its wavelength, and in the case of an atom, this wavelength is proportional to the region of space over which the atom is smeared over. But why does it look to us as though atoms, or rather the objects they make up, have single locations in space? The key reason for this comes from the same principle prohibiting atoms from having absolute positions. It states that the faster an atom is moving, the shorter its wavelength becomes, which we can rephrase as, the higher the temperature, the shorter an atom's wavelength becomes, because temperature is just a measure of how fast atoms are moving. So objects appear to have single locations in space because the temperatures we experience are high enough that atoms' wavelengths are far too small to have an effect on our perception of the world. But of course, we physicists get bored with the everyday perception of the world, so naturally we begin to wonder, what if we cooled down atoms so that their wavelengths became stretched out? Could their wavelengths become large enough to have an observable effect on reality? Well, let's take a gas of say hydrogen atoms and begin to cool it down. As the gas approaches temperatures much lower than we experience, the wavelengths of the atoms become stretched out so much that they eventually overlap. What could this mean? Well, think about what would happen if you were to smudge two identically green lines of ink together. They would merge into a single larger line, which has exactly the same characteristics as their individual lines did. The idea behind this scenario is analogous to the overlapping of the hydrogen atom's wavelengths. When the wavelengths overlap, the atoms lose their individual identities to become a single larger entity, which still has the characteristics of a single hydrogen atom. This superatom of sorts is known as a Bose-Einstein condensate, and it can exhibit properties so extraordinary that it's regarded as its own state of matter. One of the most remarkable properties Bose-Einstein condensates can exhibit is called superconductivity. Superconductors can be formed by different types of atoms that have undergone Bose-Einstein condensation, and their defining trait is that they provide precisely zero resistance when an electrical current passes through them, meaning that currents can theoretically be transmitted over infinitely long distances without any loss of energy. As a result, superconductors have a very promising future in massively boosting the efficiency of energy transportation to help transform us into a much cleaner society. Thank you for watching.